Hi everyone, and in this video we'll discuss particle spam optimization, continuation of previous video. In the previous video we have discussed about spam intelligence, introduction to PSO, original PSO algorithm, global best PSO and local best PSO, a part of original PSO, and PSO parameters we have discussed. And in this video we'll discuss about algorithm aspects, basic variations. So now we'll start with algorithm aspects. So since already we learned and it will be easy, little parameter variation has been carried out to explain the basic algorithm. First step is we'll create the population of agents, that is particles, uniformly distributed over X. Evaluate each particle's position according to the objective function. If a particle's current position is better than its previous position, update it. Determine the best particle and update the particle's velocities. That is, your new velocity is equal to the old velocity, that is inertia, social influence. See, inertia is the VI of t, and partial influence is C1 into U1 into PB, that is your best neighbor position minus current position, plus C2 into U2, that is the social influence parameters, GP is the global best position, minus PIT is the current position. Now, move particles to their new positions by using a update equation, that is Pi of t plus 1 is equal to PIT plus VIT plus 1. Go to step number 2 until stopping criteria is satisfied. So come over here and then repeat this process till all the stopping criterions are satisfied. Now we'll continue the algorithm. What is the particle velocity? Particle velocity, there are three velocities available. One is inertia, then is personal influence and social influence. What for these velocities are used? Let us see. First one is the inertia makes the particle to move in the same direction and with the same velocity. I told you already, if already there is some known velocities there, the inertia, the first parameter, will contribute the particles to move in the same direction with the same velocity. The second one, the personal influence. It improves the individuals and makes the particle return to the previous position better than the current position. It is conservative. Next, last one, social influence makes the particle to follow the best neighbor direction. So as we discussed, the first one is to continue the same direction. Second one is to incline with the respect to incline with the individuals, and then the third one is the incline with the neighbor direction. So now this equation again is divided into two parts. One is called intensification, the other one is called diversification. What is intensification? Intensification is nothing but explores the previous solution, finds the best solution of a given region. So it is just to explore the previous solutions, the previous locations of the previous positions of self anti-colony span, that is self-experience and colleague experience will be used. The experience means past. From the past information, it try to find the best region, best solution, best point, that we call as intensification. The next one is diversification. What is diversification? It searches a new solution, finds a region with potentially the best solution. So with respect to the previous voltage, previous velocities, it finds the next best solution. Next, so how the algorithm is been working? First of all, you have to initialize this span. Then the particle position has been fixed. The particle position is x of 0 equal to x min comma j plus ri of x max comma j minus x min comma j. J is varies from 1 to n minus 1 or 1 to n nx and I is varies from 1 to ns. So initially the velocity will be vi of 0 will be equal to 0. Initially the personal best position will be yi of 0 is equal to xi of 0 itself. So this is the initial condition. Then we need to find the maximum number of iterations, and acceptable solution has been found, that is function of f of I should be less than or equal to modulus of function of x minus epsilon. No improvement is observed over a number of iterations, then that may be because of the average change in a particle position is very small. Otherwise, if the average particle velocity over a number of iterations is approximately 0, that means there is no movement and it is stationary. In that case, even though the iteration increases, there won't be any improvement. So it is that is the reason it might be not giving any improvement further. Objective function slope is approximately 0 because it's not moving. So f dash of t is equal to f of y cap of t minus f of y cap of t minus 1 divided by f of y cap of t. So in this, the slope will be approximately 0. If f dash of t is less than epsilon, then the swamp will converge. So there is an animation. You can see this is the global optimum point, and the particles is slowly converging to this. One more animation will take example. So you can see here, this is the maximum point, and these are the different locations. The our particles are present, but slowly it will be converging, will be moving towards the maxima point. Yes. The next is, and in the beginning we learned that there are different topology as are available, star topology and ring topology respectively for your local and global best PSO has been available. Apart from the star and ring, there are wheel, pyramid, 4 clusters, 1 human structures also available. These are some of the social network structures. Next, let us see the variance. The variations actually just to improve the basic PSO it is being used. In what point of view want to improve the PSO means the speed of convergence rate as can be improved, the quality of the solution can be improved. In these 2 point of view, you can improve the basic PSO. But the velocity clamping and inertia weight, constriction coefficient are the 3 different variations present. Let us see one by one. What is velocity clamping is? See, there is always trade-off between exploration and exploitation. Exploration is nothing but just to explore different regions of such space. Exploitation is nothing but concentrate the search around a promising area. So good optimization algorithm should balance these two contradictory objectives. The velocity update equation is the main equation that will be giving you the balance between these two. So velocity quickly explodes to a larger value, then the particle will have a large position update. The particle will diverge, it won't converge. So should control the global exploration of particles. The velocities clamp to stay within the boundary constraints. That means the Vmax, j denote the maximum allowed velocity in the dimension j. So ensure that it goes clamps up to the maximum boundary constraint, that is Vmax, j. So the velocity Vij of t plus 1 can be written as Vij dash of t plus 1 in case the Vij dash of t plus 1 is less than Vmax j. If it is otherwise, that is your dash Vij is greater than Vmax j, then we'll replace the Vmax itself Vij of t plus 1. So large value of Vmax comma j facilitate global exploration. Small value converges local exploitation. So if Vmax j is too small, the swarm may not explore sufficiently beyond the local good region and increase the number of time steps to reach an optimum. Swarm may become tapped into a local optima. So if Vmax, the velocity is very small, too small, it may not explore much. It will increase the number of time steps. That means smaller steps it will take. So no more number of time steps will be there. It will be tapped into a local optimum. If Vmax is large, the risk of possibility of missing a good region will be there, and particles may jump over a good solution, and hence, but at the same time, the particles are moving faster, more faster. So, what to do? There should be balance. There should be balance between the fast and slow moving, and there should be balance between exploration and exploitation. So for that, the Vmax of j can be determined, the upper limit, the maximum velocity, the clamped velocity can be fixed as alpha del into x max comma j minus x min comma j, where the del is the problem dependent. It is a value taken from 0 to 1. And so that will decide, and because of this parameter, your velocity clamping maintains the balance between too fast and too slow, as well as exploration and exploitation. Now we'll move to the second type, that is inertia weight. It is again induced by Sri and Elberhard and control the exploration and exploitation abilities of the swarm, similar to the previous one, and eliminates the need of velocity clamping. So here the parameter will not be applied to the other two, that is the equation second and third term will not have any weight, only the first term will be having a weight. So control the influence of previous flight direction to a new velocity. So you can see the weight is only applied to first term, the second and third terms are left free. So the value of W is extremely important, that ensures the convergence behavior, and that also takes care of the trade-off between the exploration and exploitation. If the W value is kept very high, much greater than 1, the velocity increases over time and the swarm will diverge. And the particles fails to change the direction. Whereas when W is less than 1, the particle decelerate until their velocities reaches 0. Decelerate until their velocity reaches 0. So these will guarantees the convergence particles trajectory, and if this condition is not satisfied, divergence and cyclic behavior may occur. So dynamic inertia weight approaches linearly decrease. We start with W of O equal to 0.9 and final weight inertia will be W equal to 0.4. So the W equal to W of 0 minus W of nt into nt minus t by nt plus W of nt, where in this case nt is the maximum number of time steps, W of 0 is the initial inertia weight, Wnt is the final inertia weight, and Wt is the inertia at time step t. And sometimes this may be randomly adjust. That time the W can be taken as C1 into R1 plus C2 into R2. In this case, the W value will be ranging from 0.72 to sigma. Nonlinear decreasing, in that case Wt plus 1 will be equal to Wt minus 0.4 into Nt minus t divided by Nt plus 0.4. This is how the new weight values, are calculated. Inertia weight values are calculated. The last one, constriction coefficient, it's a similar to inertia weight, so it is also balanced between the exploration and exploitation trade-off. The velocities are constricted by a constant x and referred to as the constriction coefficient, and you can see the equation. The entire three terms are multiplied by the parameter x, and k is the and then the x is given by 2k divided by a modulus of 2 minus pi minus square root of pi into pi minus 4, where pi is given by c1 r1 plus c2 r2, where k is a value taken from the set 0 to 1. K controls the exploration and exploitation. If k equal to 0, it fast converge and local exploitation takes place. And in case k is approximately equal to 1, then slow convergence takes place. High degree of exploration will take place. Usually k will be set to constant value, and first k set close to 1 and decreasing to 0. Constriction approach equivalents to inertia weight approach in case if w equal to x and phi 1 is equal to x into c1 into r1 and phi 2 is equal to x into c2 into r2. So that's a special condition of your inertia weight. The third one is a special case. So there are, apart from these three, there are different other approaches also available, like active target PSO, adaptive PSO, adaptive mutation PSO, adaptive PSO, guided by acceleration information, binary PSO, etc., available. And then in last, we'll see the advantages and disadvantages. And the advantages, when you see, are the algorithm characteristics you see. It is inextensive to scaling of design variables and simple to implement. It can be easily parallelized for concurrent processing. It is derivative free, and it is very few algorithm parameters, and it has got a very efficient global search algorithm. And drawbacks, there is a tendency to fast and premature convergence in mid optimization point. Slow convergence is refined such stages. These are the drawbacks of PSO. Thank you very much. Happy learning. Bye bye.